Hey everybody, welcome back. It's Mr. G again. Today we're going to be talking about Norton's Theorem. So we've already talked about Thevenin's Theorem, so that was a lecture we had in class. And today we're going to be talking about Norton's Theorem. So, before we do Norton's Theorem, we need to do a little backtracking and talk about a voltage supply versus a current supply. So if you don't remember what a voltage supply is versus a current supply, or you're new to this and you want to do some research, you can do some checking up. Our textbook is Principles of Electric Circuits, Conventional Current Edition by Floyd and Buckla. We use the 10th edition. And if you looked at chapter 2-3, it talks about the voltage supply. Talk about the current supply in chapter 2-4. So if you want to go back and do a little bit of research, basically you'll find out what the difference is between the two. But in general, a voltage supply is a constant voltage that's being supplied to a circuit, whereas a current supply is a constant current that is being supplied to the circuit. In a voltage supply, the current is what changes throughout the circuit, whereas in a current supply, it's the voltage that would change depending on the change of circuit. So, one other difference, if we looked at Thevenin's versus Norton's. So Thevenin's is actually an equivalent circuit using a voltage supply, whereas Norton's is an equivalent circuit using a current supply. So in the Thevenin's circuit, the voltage is actually divided up between the two resistors. So we've got a series circuit, and the voltage here is divided up between those two resistors. In Norton's, we have a constant current source. So the current leaving the source remains constant, and it gets divided up between the two resistors. So we've got Norton's resistance and then our load resistance. So in this parallel circuit, that current leaving the source gets divided up between these two. So Thevenin's is an equivalent circuit using a voltage supply. Norton's is an equivalent using a current supply. So again, if you're unfamiliar or need a little bit of a review on what a constant current supply is, you can go back to our chapter 2-3, look at voltage, and chapter 2-4 and look at the current supply. So in Thevenin's, which we've already covered, so Thevenin's equivalent theory, basically we're taking a complex circuit, simplifying it down so that we have a voltage source, two resistors in series. So there's a procedure we go through to convert this into this. So we've covered that already in class. There are also notes on Blackboard that help you go through that procedure. If you needed another set of references in the textbook, again, so in our textbook on chapter 8-5 is review on Thevenin's theorem. So again, it's a procedure that we go through in order to convert a complex circuit into something as simple as this. Norton's. So Norton's circuit. The concept again is to take a complex circuit like this and convert it into something simple like this. One constant current source, and then we have two resistors in parallel. After we get through this lecture, if you need some more review, you can find Norton's Theorem, chapter 8-6 in, again, our textbook. So, what is Norton's Theorem and why do we need it? Well, basically the idea is we have a circuit we have identified one resistor in our complex circuit, which we're going to call the load resistor. This becomes the focus of study for this particular circuit. We want to look at all the conditions around that particular resistor. So we want to look at the voltage that goes across that resistor. We want to know the current that goes through that resistor. We would like to know maybe about the power dissipation of that resistor. So we can do that by solving this complex circuit. But what happens if we want to change the load? All of our calculations all change. Where in Norton's, what we do is we take an equivalent circuit. So the equivalent circuit is actually equal to this without the load. So that becomes this. And the load gets attached later. So now what we can do is we can calculate Norton's equivalent circuit once, pop in as many loads as we want, do all the calculations, and those values would be equivalent to those resistor values that are in the original circuit. So again, power, voltage, current would all remain the same in this circuit and this one. This circuit, it's much easier to calculate than in this circuit. So that's the idea. We're going to simplify this circuit down. Everything inside this red circle here is going to be simplified down to two components, a constant current source and a Norton's value of internal resistance. And then all we're left with is two resistors in parallel and a current source, and we can easily figure out the current divider, and we can figure out voltage via Ohm's law, we can calculate power, all based on this resistor. Very, very easy. Okay, so again, the voltage that's crossed this resistor, the current flowing through this resistor, the power that this resistor dissipates would be exactly the same in this circuit. So these two are going to be equivalent with respect to the load. Okay? So when you're looking at the load, these two circuits are equivalent with respect to the load. So let's take an example of Thevenin's circuit, or sorry, Norton's circuit. So what we're going to do, we're going to solve for this one. So I've got this complex circuit here, which is basically I've added some numbers to the circuit that we've been looking at. And what we're going to do is we're going to go through a procedure that's going to turn this into Norton's circuit. So there are two calculations that need to be done. One is for Norton's resistance. So when we look at Norton's circuit, it comes to a resistance value we have to calculate and a current value we need to calculate. So what we're going to be doing, first we're going to be doing our Nortons. It doesn't matter which one you do first, because both sets of calculations are completely independent of each other, have nothing to do with each other, and therefore you always start off at the beginning circuit. So in this case, we're going to calculate Norton's resistance first. Now, one nice thing is, if we've already studied Thevenin's, you're going to find out that Thevenin's resistance, so resistance for Thevenin, is exactly the same as resistance for Norton. So the procedure is exactly the same. So what we're going to do is we're going to take our circuit, we are going to solve for Thevenin's equivalent resistance, which just happens to be the same as Norton's equivalent resistance. So both of those numbers are the same, it's the exact same procedure. We've already looked at Thevenin's. Same procedure for Norton's. So here's what we're going to do. we're going to take this circuit and I'm going to go step by step and we're going to solve for our Norton. So I move that out there. So let's take our circuit. So we have our 3 resistors here. We have another resistor here, another resistor here. This is the load at 1K. This is our 4 at 1K. This was 1.5K, 1.5K, 1.5K. And this was R1, R2, and R3. The supply was 12 volts. So now what we're going to do is I'm going to take that circuit and we are going to solve for Norton's equivalent resistance. So the first thing we must do is remove the load. When we are solving, if you remember again, inside that circle, we're looking at solving for R Norton and I Norton. In order to find those values, we look here, this is where we get them from. You'll notice that RL is not inside that circuit. RL is not inside that circuit, or that circle. So what we need to do is we need to remove RL from the original circuit. So this circuit actually translates into something that looks like this. So we have resistor, resistor, resistor. We have resistor. And this is where RL used to be. So now this is R1, R2, R3, and R4. So this is where RL used to be. So we remove the load. I always like to mark it with A and B, so we have points of reference. So remove the load, mark it AB. The next thing that we do in the procedure is we are going to actually get rid of the source. So what we need to do is we need to actually short out the source. So in theory, we just take a line and put it through the source like that. Pretend the source is not there. We're shorting out the source. So now, if we were to build this circuit here with the source shorted out, we just put these 4 resistors in this configuration and we put an ohm meter and we measured from A to B. So RA to B. If we measured from A to B, that would be R Norton. So again, the procedure is remove the load, mark it A and B, short out the source. So we're going to remove the load. We're going to mark it AB. And then we are going to short out the source. So short out the power supply. Then you find the resistance from RAB. So you're finding the resistance looking back this way. That is equal to R Norton. So that's the procedure we're going to follow. So again, remove the load, mark it AB, short out the source. So what we're left with are these resistors here and this one here. So when I look from part A and B and I look back, I'm going to see that we have R1 in parallel with R2 in parallel with R3, all in series with R4, and that's what is going to be RAB. So these 3 resistors are in parallel with each other and in series with this one. So RAB is R Norton, and we have these 3 in parallel plus this one. So that works out to be 1.5k in parallel with 1.5k in parallel with 1.5k plus 1k. These three in parallel work out to be 500 ohms plus 1k. So therefore, RA to B is actually equal to 1.5 kilo ohms. And that is our Norton. So, we follow that procedure, we're going to come up with 1.5k for this example. So what we do is we go back to our original here, and we have just found our Norton. So what we're going to do is we are going to build Norton's equivalent. So the first thing that I did in the procedure was I removed the load. Might as well just put it right here. So RL, 1K. This is Rn. We just calculated that to be 1.5K. So what's next to do is I Norton. So I Norton is our next calculation, and there's a full procedure for that. So we're going to go back to the original circuit. Why are we going back to the original circuit? Because I Norton has absolutely nothing to do with R Norton. They are completely different calculations and must be done completely separate. So we're going to go back to the original case, and we got 1.5K, 1.5K, and 1.5K. That's R1, R2, R3, and this was the source, and this was 12 volts. So now we're back to the original circuit. Now what we're looking for is I Norton. So I Norton. So the first thing that we must do is we must remove the load again. Again, none of these values can be calculated with the load in place. So we're going to take this circuit, remove the load. So we're going to take this same circuit, I'm going to swap out, remove the load. And we're going to mark it A and B. So where the load used to be, is now going to become A, B again. So now we're at this point again. So the load has been removed and we are there. What we need to do now is create a short circuit from point A to point B. So just pretend there's a wire there. In this circuit now, if we can calculate the current that is flowing through that little piece of wire, that will become I Norton. So again, the procedure is remove the load, mark it AB, then you want to short A to B, and then find the current in that short. And that current is I Norton. So again, we've removed the load, marked it AB. We are now going to place a short between those 2 points. if we can find the current between those 2 points, so whatever current is flowing through that wire, that is I Norton. So in this particular case, again, we look at these resistors. So this is R1, R2, R3. This is R4. This current that's flowing through there in this example actually happens to be I total. So that's for this example. So if we, for this example, were able to calculate I total, that would be the current flowing through that line. And again, this is just for this example. So I total, according to Ohm's law, is voltage total divided by resistance total of the circuit. So we know that the voltage total is 12 volts. We need to figure out what the resistance total is. So now we look here and we say, oh look, there's this resistor in parallel with this resistor in parallel with this resistor plus this resistor. So again, that becomes 1.5 in parallel 1.5 in parallel with 1.5 becomes 500 plus 1K. And that is 12 over 1500 or 1.5K. And I total in this particular case is going to be 12 divided by 1500. So that becomes 8 milliamps. So I total in this circuit is 8 milliamps. That just happens to be, for this example, I Norton. So now we've figured out I Norton. So we'll go back to our original circuit here like this, and we put this as 8 milliamps, I Norton. So now we have completed Norton's equivalent circuit. So here's the original. Here is Norton's equivalent circuit. Now, if this was true, so that means if these two circuits are the same, then that means that the current through RL and the voltage across RL and the power of RL must be the same in this circuit as they are in this circuit. Okay, so again, the current flowing through this resistor must be equivalent to the current flowing through that resistor. The voltage drop across this resistor must be the same as the voltage drop across this resistor. The power that's dissipated as heat in this resistor must be the same as this resistor. If those three things are true, then these circuits are equivalent. So what we're going to do is we're going to quickly solve for current, voltage, and power in this circuit, current, voltage, and power in this circuit, and then we will be able to determine whether or not these two things are true. So for this circuit, the current that's flowing through there happens to be I total. The current flowing through there is I total. So we can find it by saying Vs divided by RT is I total, and that just happens to be, in this case, the current through the load. So if we solve that real quick, we got 12 volts divided by, and our total resistance is this one, and this one in parallel, added to this, added to this. So that's 500, 1500, 2500. So we got 2500 ohms, I total. And that happens to be equal to 4.8 milliamps. 4.8 milliamps using Ohm's law. So Ohm's law will say that the voltage across RL is the current going through it times the value of RL. So that becomes 4.8 milliamps times 1K. That is equal to 4.8 volts. So the current is 4.8 milliamps in this circuit. The voltage across that resistor is 4.8 volts. If we do a quick little multiplication, we can find that the power in RL is going to be equal to 4.8 milliamps times 4.8 volts. So power is voltage times current. So we'll just take this value here, 4.8 milliamps times 4.8 volts, and we get 23 milliwatts of power. So 23 milliwatts of power. So that's using this circuit. Okay, so that's using this circuit. Now we're going to calculate the same values, but using this circuit. So we got 8 milliamps here. We need to find out how much is flowing through here. We can use the current divider formula. So the current divider formula says that IL, so the load current here, is equal to the I Norton current times, we've got the total resistance of the circuit, so R total, divided by RL. So that's the current divider formula, and that works out to be 8 milliamps. It's 8 milliamps. Our R total is 1.5K in parallel with 1K, and that works out to be actually 600 ohms, divided by RL, which is 1K. If I do that math, so again, I get 600 ohms divided by 1,000 ohms times 8 milliamps. 4.8 milliamps. So 4.8 milliamps. So using this circuit, calculating the current, I get the same value. Ohm's law will tell me again that if I want the voltage across RL, it's equal to the current times the resistance. So that is 4.8 milliamps times 1K, giving me 4.8 volts. That voltage, calculated this way, is exactly the same as this voltage, calculated this way. And if we take the same current and the same voltage, hey look, same voltage, same current, multiply them together, we're going to get the same power. So all of these values work out. The current going through this resistor is exactly the same as the current going through this resistor. The voltage drop across this resistor is exactly the same as the voltage drop across this resistor, and the power dissipated in this resistor is exactly the same as the power dissipated in this resistor. So, with respect to the load, these two circuits are equal. All right, so that's our procedure. Again, we have proven that these things are indeed equal with respect to the load. So, there are plenty of questions for you to practice. Again, Chapter 8-6, Norton's Theorem, in our textbook. For your reference, I have also put together a procedure for solving Norton's Theorem. So solving Norton's circuits. So the procedure that I just went through is here step by step for calculating R Norton as well as for calculating I Norton. So these notes are available on Blackboard. There's also a set of instructions for solving Thevenin's equivalent circuit as well on Blackboard as part of your class notes. So the procedure is there, step by step. So in case you didn't pick it all up when we just did that example, the procedures are there. There's plenty of questions in the textbook for you to do. Again, chapter 8-6 in our textbook, and that'll walk you through solving Norton's theorem. So equivalent circuit from here to here. So that is Norton's theorem. I hope that helps. Everybody take care, and we'll see you again next time.